Okay, so we ended last class starting to briefly talk about dual read, single write SRAM. These are what are used in registers. The SRAM is used in data memory and in instruction memory, but dual read, single write SRAM is specifically used in registers to be able to do multiple portions of the R-type instructions. I have initial error checking step here, where I have if write is true and either of the read statements are true, then it shouldn't be allowed to do anything. Otherwise, if you're going to write, you write to the cell here. So we had created this SRAM function that updates cells. Otherwise, read, you get data 0. Remember, we passed cell as a pointer, so we use an arrow. And if read 1, there's no else if because we don't have the dual read, single write capabilities. So now I've created a test function. I've initialized a SRAM cell. We created a function last class that's initialized SRAM. So please don't turn in your homework while I'm lecturing. And then I have initialized some read values and some write values and initialized the test cell, bit line, and word line. And then here I actually begin the process of doing a number of test cases. So, sorry about that. So then we actually run the dual read, single write SRAM here, print it out, and then print SRAM test cell. So I have a function print SRAM, which I introduced last lecture here. Just one simple fprintf statement to be able to do this. Make sure when you do your coding projects that's due this Sunday that you actually have the values retained. Do not write a function that simply takes in values, performs an operations, and prints them, because remember, you're building on these to eventually build a full mixed data path. So if you miss those, you're going to be losing out on points. But more importantly, you'll have to go back and do work in order to be able to get your final project working. So that's why I have these print functions here to be able to do these. And then I print out a few cases, and this is the program output. As we expect, we get all these correct values here. So, all right, so here's what we're going to do. In order to do this, in order to properly implement a memory element, we got to learn about reading in from files and writing to files. So in your project, the way you're going to represent long-term memory storage is by reading in from a text file, having your data memory hold that value, and then the last thing you're going to do is write to the file to be able to update it. When you do your final project, when I'm going to run your code, I'm going to look at your first part of your final project is to go through a code sample, write it up, and initialize the file function. Like these, the file should say this, they should say this, they should say this. I give you your feedback, correct them, and then for the second part, you actually will have everything built up such that you'll run it, I'll run your code, and I'll see what the final functions look like. And then, so the whole goal is to be able to update it by doing these operations. So we have to learn to read and write from test files. So I've come up with a couple of steps to be able to read and write to a file. We're going to be initializing a file pointer called file star. You can call it FP. You're going to do 3. I would, it is uppercase. This file uppercase, that's important. We're going to be doing standard IO. And you can do like star data memory, star instruction memory, star registers, FP or whatever. Like so. Then you want to create a character array with a file name, file.text or whatever. And then you're going to use this specific function here, FP. So you don't have to, you're actually setting the file pointer, because we're not using a star. So FP equals, the function is fopen, file open, file name, which means in this case, I had set file name at char star, file name equals, for example, the file dot text, right? So that's just step 2. Step 3, actual file name. And then the next thing you want to do is you want to have these quotes that say R. R is for reading. When we get to the next TGO to talk about writing, W is for writing. And there are a lot more, read, write. There's multiple ways you can do this. But in this course, reading in everything, performing the operations in the procedural C language, and then writing the results back to the output is going to be sufficient for this course. Yes?
Do those functions come from the standard library?
Yes, standard IO. Any other questions? Okay. So test that the file exists using if file pointer equals null. So the first thing you're going to want to do is you're going to test that the file is actually there. Because if you don't, you'll get a nice little nasty compiler error or it'll spin. So you don't want to try to load up a bunch of nothing into your file. And then once checked, you're going to read in each line using fscanf. And we're going to be going over coding examples of how to do this. So for 4.17, for writing to a file, first thing you're going to do is you're going to repeat the exact same steps. You're going to initialize the file pointer, or if you have the file pointer initialized, you don't need to reinitialize it because it's already pointing to the file. Use fp equals fopen file name, comma w, where file name is a variable, array of characters, and then w means write. Test if the file exists using if fp equals null. And then once checked, write each line using fprintf. So this is where what we've done before in the class comes into play. So before now, we've been doing fprintf standard out or standard error, depending on what you guys have been doing. So now we're actually going to be putting in your file pointer there. So you do this, you'll actually be writing to the file. Okay, so I'm going to go past 416 just to be able to use 417 in the back. So I've written this function here. And so first I've created file. I called it ifpreg input file pointer register. So just like step 1, I've initialized my file pointer. Step 2, I've initialized the file name using a char array. Char star file name equals registers.txt. What I call this file. And then like step 3, ifpreg equals fopen file name r. So here I have file name. You can just pass it like normal. I know it's a char star array and you don't have to put any pointers there. And then this step here is that 4th step where I was talking about doing the file checking. If ifpreg equals null, that means the file does not exist. fprintf standard error couldn't open %s exiting program. So %s is printing a string, which is in C an array of characters. So I've done %s and then file name, and that allows me to be able to tell the user that the file does not actually exist. So trust me, this will. The reason I'm having you guys do the TGOs so that when you write it out, I do this step, that will save you tons of trouble because it will print out the error telling you where your issue is. You're reading it in, you can spend hours trying to figure it out and then not knowing the file just isn't there. Okay, in this case, in the registers, which you'll start to learn about next section, there are going to be 32 values. And so here, I have printed to the user reading in values from the file name, initialized int I. So I have a value pound defined called numregs, which is 32. And that's an I++. So my character input string, so first I initialize an input string where I'm going to be storing the input from the file. I've done that with a palette, bits, and size of character. Now, a student come into office hours and was asking about this, so I want to point out that this is the actual code I want you to put in. It's not some sort of, placeholder. Like if you put in size of car, that's an actual function in C that indicates give me the size of a character, return that, and allocate the value with initial zeros. Then I did the same thing. I created an array of booleans. Input booleans equals bool star, calec, bits, comma, size of bool. And then I do this. fscanf. So it's just like fprintf, except it's fscanf. Now scanning means I'm scanning the file, whereas printing means I'm printing to the file. So I've input my pointer to the file. I've indicated what I'm expecting to read. In this case, I'm expecting to read a input string, and then I'm assigning it to this input string here. So what's happening is it's reading the string and putting it in there. Whereas in fprintf, you're taking this value and you see that and you're printing it to the function. So that makes sense. So in scanf, it's going this way, whereas in fprintf, it's going that way. And then I have this function that I've used again. I have an input string and an input bool, where a few of you have already coded this up, where it goes through and iterates through the Boolean array and then initializes it. Where an input string and initializes the Boolean array. Now the next step is to put the values in the current register. So here, as you can see, we're actually looping through all 32. So here I have some sort of input Boolean now. And so I'm setting the bit line of the current register. So I'm iterating through each bit in the register. So I have 32 registers, and each register has 32 bits, right? So what I'm doing is, for j equals 0, j is bits, j++, I've initialized the bit line of the register to be the input value that we're currently at in the array, in the input bool array. So I've read in the values from the file. I have a 32-bit value. I'm going through 0, and then I'm initializing the registers in that manner. And then I'm setting the word line equal to 1. And then I have my cells, and then I update the SRAM. I use my function here to actually update the values. And so I'm doing that for every single SRAM cell, and then I do it 32 times for each register. Now, why do you think I want you to code it up this way, other than I'm trying to torch you, because that's what professors do? Do any of you know what a bootstrap program is? Okay, so the whole in operating systems, for those of you who are CE, you're eventually going to cover this. The bootstrap program is when you start up a computer, you know all those commands that are going up. That's what's known as a bootstrap program. It's the program that starts you up. So the program runs the moment. So the computer runs the moment the computer starts. And so what you're doing here is kind of initializing a portion of the bootstrap program. This is where we're talking about the compiler-driven encoding of the micro engine, where the compiler takes from the bootstrap program this actual bit values that says, I want these values in instruction memory, I want these values initially in my data memory cache hierarchy, and we need to initialize the registers to these values. So what you're actually doing is you're going through, as the computer does, to each individual SRAM and initializing values for the program to start. So here, as you see, we know there's 32 registers. So we're going through each register, and then here in this loop, you go back to, so in this loop, we're updating each individual SRAM cell. So here the registers contain a set of cells, and then I actually run SRAM to actually initialize it. And then once I'm done with each loop, I free my input bool. Let me scroll up a little bit for those of you in the back. Remember, whenever I allocate memory, I want to deallocate it the moment I'm done with it. So in each loop, I'm allocating a new input bool. And then after I'm done here, fclose. This function fclose deallocates my pointer to the file. So when I'm done with this file, I'm done reading in my files from the file. And I close off the pointer until I need to use it again, which point I can do another file pointer. Does this make sense? Okay. So here, I've actually created a Boolean array. So the array I is equal to current register, so I can get an array of Booleans. So I wanted to show this as a, oh yeah, now I remember why I wanted to do this. Because I'm getting a lot of questions during office hours about pointers, arrays, so on. So this is a really good example of how pointers work and arrays work. So here, I have this register value, right? This register is a type def that I've defined that contains 32 dual read, single write SRAM, because each one does that. So I am passing one register to the function. I'm also passing a pointer to the base pointer of the array to the function as well of 32 Booleans. So then I go through each Boolean, and I'm taking the register current cell, so it's going through each cell, and then telling me what the Q value is, because the Q value is the actual value, right? So give me that current cell, so it's going to go through each cell, give me the Q value, and assign that to the array, and return it. So here, the reason, now here's the question, see if this is the $1 million question, see if you guys understand pointers and arrays. Why don't I have an ampersand here? Oh, I'm sorry, a star. Yes, right.
Because arrays are already pointers?
Correct. An array represents a pointer to a set of block in memory. So the star is telling me, find that in memory, get that, and we've deallocated it, right? This code right here is already doing that for you. Yes, Brian?
In the argument, is the star just to indicate the function that it's an array?
Correct. Now, if I was doing this, and so this is a different example. I could write the exact same function and get rid of this, right? And say, instead of the array, I could call it the bool. And so if I wanted to just get the bool, I was going to erase this for a second. So to answer that question more thoroughly, I'd have to go star the bool equals current register cell I, or I could just say 0 or initialize some value of I, right? And so if I put that, put this here, now what I've done, get rid of that loop. So let's say I call this 0. So what this means is by requiring a pointer here, I'm now an element of memory allocated in the data memory that I'm pointing to using a pointer. I've dereferenced it and done one value. So that's the difference between bool star the bool, where it's one bool, and bool star the array, where it's an entire array. By doing this array code, that's actually already doing the pointer work for you. Whereas if it's just one, you have to do the work. Hey, does that make sense? Hopefully it's clearing up pointers a little more. Okay, so I've already talked about SRAM a little bit here. I've created a type def struct SRAM. Kind of already alluded to it. Here, I've also alluded to this register. If you remember from structs, the big uppercase word at the end there is how you would refer to it in the code. So type def struct SRAM, that created every element in the SRAM. Here I've actually done type def struct and then the lowercase reg. If I have SRAM cells, bits is pound defined as 32. And then I have uppercase register here. So if you recall from up here just a moment ago, to refer to it, I use uppercase register. Now, when you're using Eclipse, it'll actually make it green. So if you're trying to define your own structs and suddenly you start referring to them and they start showing up green, that means you've done it properly. If it's not green, something's wrong. So here, I have a function where I've updated the register. Again, I'm passing an array of booleans. So I have a 32-bit array. The register's here, so I'm updating the array, and I'm updating not the array as Q bar. Got a lot of smiles, at least if touching one thing, that Q never equals Q naught, right? So current register, and then I now pass the, now I have a pointer here, which means I use the arrow here, right? So that dereferences it and allows me to get to the cells. So if you recall from up here, I didn't pass a pointer, so this dot is used, whereas now I've passed a pointer to update the register. I now use an arrow here. Now once I've dereferenced that pointer, the pointer was pointing to a set of cells, right, within the struct. So now I can use .q and .qb because now it's already been dereferenced. Now we're already going to that location. So a common mistake that I've seen students do, and when I was a student I used to think, oh, I've got a pointer and I have a struct. Now I have to do another arrow, right? That's a very common mistake. So I wanted to show that to you so you can, if you work through this and work through this code, this is a really good concept understanding. If you can intrinsically understand this code here, you really understand pointers. Before I move on, does anybody not understand any part of this? All right, cool. You've mastered pointers. All right, so now we've done fscanf. We've updated our register. We created our structs. Now I want to update my file, put it back into the file. Now what we're simulating there is by putting it back into the file, we're putting it into the non-volatile RAID arrays, which when you turn the computer off, that's information is saved. So you have, the whole point of MIPS is you want it to go fast. We have temporary local copies. And then once we're done, we put it back into the memory. You're simulating that using printf to a file. So here we have initialized the pointer again to the file. We have the char file name, registers. Right, so then, as I mentioned in the topical guide objective, I think I have somehow screwed up my pen here. All right, so what I'm saying here is IFP register equals fopen file name W. I figured out what it was. So here it's file name, and then we use W instead of R because we're writing instead of reading. And then I do the same test every time. If ifpreg is equal to null, could not exit the program. Could not open it, exiting program. And then I put in exit -1. Now, the next step, I initialize I and J because I'm going through 32 registers and I'm going through 32 SRAM in each register, correct? So then, MIPS register, I equals 0, I less than equal to number registers, I plus plus, J bits, and MIPS, they both happen to be equal to 32. Now, if Q is 0, if Q is 1, print, I have MIPS registers dot cells J dot Q if, that means I'm checking to see if the bool is true or false. If it's true, fprintf, your pointer 1, else, print to the pointer, and then 0. And then once I get to that last line, the last Boolean, I have this little, if I is not equal to numRegs -1, fprintf, pointer, return character. This allows me to go through all the way through the Boolean, get to that end, and print, and then go to the next line. Otherwise, if you don't do something like this, what will happen is you'll just have this huge string of Booleans that will be all in one line. And now I'm going to, before I go on and show you the example of how the code works, does anybody have any questions about what I've done here? All right. Okay, so here I have my file hierarchy. I have MIPS, arith, I have synchronous, and memory. So I've created these memory.h files to put that in there so I can start accessing my data memory, my instruction memory, and so forth. So then you're going to have a ALU, you're going to have a memory, and you're going to start seeing it, you're going to start doing control functions. And once you start doing these control functions, then you'll be able to build the full data path. So here I've initialized, the first thing I do is I create registers. Eventually when you do your final MIPS data path, you're going to create registers, you're going to create data memory, you're going to create instruction memory. And you'll be able to initialize and allocate memory for all of those. So we're starting to get to the point where we're now starting to MSI level of transistors, right? I'm sorry, we're now getting to LSI because we got 30. Yeah, and we're getting to LSI. So initialize all the SRAM cells. So I go through all 32 SRAM cells in this one register and initialize it. And then initialize the register write bit. So remember I had that initialize registers function. Just pass the register there. So here's a good question because I actually haven't covered this yet. Why did I do, so I've created an array of registers. I did numRegs +1. Why do you think I did that? So just 32 registers, I created a 33rd there. No, this is an array of registers. So I've created a struct, so it's not a signed bit. This is 32 registers, not 32 Boolean. Okay, I'm guessing. Okay, so in an array, what C has done for you is that at the very end, it has this character at all arrays. So you allocate an array of 32 bits, it automatically does that. To do it for a struct, you have to add it in there for you. So you add in a third one. By adding in this extra one, you won't have any overwrite issues. Because now that we're dealing with pointers and we're trying to increment and decrement pointers, you want to be able to make sure that you have a space in there. Okay, so then I use that function that I came with, print registers. And then I have here now, okay, so I now have now adding registers. So I've created 3 characters here. Let me scroll up for those in the back. So I've created 3 character arrays. I've char read reg 1. I've char read reg 2 and char write register. So if you recall, we have 32 bits, and I'm just indicating which one I want to read. So in this case, instead of just saying 16, you got to indicate which value you're doing by using Boolean, right? Because we are doing things in machine code. So here, this is the 16th bit that this value is a 1. This value here. In this case, this is the 17th bit. In this case, the write register, this is the 18th bit. So that means I want to read the 16th value. I want to read the 17th value. We're going to do something and put it in the 18th value. This is what's known as an R-type instruction. We'll go with that in section 5. So if I were to have this as 16 again, then the dual read single write would be reading the same register twice. So it would be J equals I plus I or something like that, right? That's where the dual read single write capability comes into play. And so, as we do every time, allocate the memory for input storage or input arrays. And then I call my char array to bool array function 3 times for register 1, register 2, and char on write register. And so the last thing I do is this, I call it read data here. So here's what happens with read register and read data. So when you go through this, you're going to kind of like work through the code and notice my comments. When we start getting, especially when we start getting a data path, this will make more sense. But the whole idea is I take a 32-bit value in, it finds one of my values in the registers that indicates which register I want. That goes to the specific register. The register is holding a value, right? So I have the location and then its actual creamy center. I'm allocating those values that we're going to be getting out once we read and putting those into their own booleans. That makes sense? So I actually get read data 1 and then I print the values out to the register. So here what I'm doing is I'm going through I equals bits minus 1. Remember, the least significant bit of the array is here, and we read this way, but least significant bits and most significant bit is the other way. They had a group come in talking about iteration. So this is why I do it this specific way, is to be able to properly iterate through the array. So here, if bool read register is I is true, then I want to get that bool away. So this means is you're going to go through 0, 0, 0, 0, 0, 0. You're incrementing I, and eventually you're going to get to a 1, right? Once you get to that 1, then I want to get the bool array using that function that we wrote earlier. I pass the registers, the register pointer, bits minus I minus 1 passes the specific register. I now have bool read data 1, and it returns the value. Remember, it's a pointer to an array. So this value is going to be updated in the function, and now we come back out. And then I remember earlier I had this function print 32-bit. It just goes through, iterates, and prints it out. So now I read register 1 and contains read data 1. So this is a check. So I say I found 16 and it contains a specific value. And then I did the same thing for read data 2. So in this case, read data 2 is actually the 17th register. So it's going to loop through. So this is what's physically happening in the digital system, right? It's physically happening. It's iterating, gets to that 17th bit. It goes, I want this specific value. Gives me that value. And then we use that get bool array function that I wrote earlier. And then I print it out again. Now here's what I do next. I initialize my carry bit to false. and then I call our 32-bit adder, which we've previously written. So I have bool sum. It's a pointer to a 32-bit array of bools. It's going to be equal to the result of my 32-bit full adder. I'm passing bool read data 1, bool read data 2, and that carry bit. So that carry bit, by using the ampersand here, the last carry out will be passed to us, right? So we can actually use that as the carry flag. If you remember from section 3 with the arithmetic logic unit, where we have an overflow, we have a carry flag, and we have 32-bit outputs. Now we're starting to get those values. So this is how we can create a register and get results. So now we have our sum, and now we're going to have our addition results. I had written a function, 32-bit test print, where I read in the inputs, the carry bit, and the resulting sum, and it actually printed the values out to the output. Now, I use that update register where I take the 32-bit sum value. I'm sorry, one last thing I should say this. So remember I had 16, 17, and 18 for my 3 read data 1, read data 2, and then, read register 1, read register 2, and then a write register, correct? So now 18 is going to be equal to, it's going to find the 18th register, and then it's going to update the register using that specific register. I'm using the ampersand because we want the result back, and then passing the 32-bit sum. And then printing the registers, I can actually go and print them all out. So I can go to print register, just iterate all through. And then I have that function update register that we had written earlier that iterates through them all and then writes to the file, if you recall. And then last thing I do is I free all my allocated memory. So here I want to show you the results. So here so my initial values, I didn't have, I've marked these, but in the .text file, all I had was these values here, but I've also put line values to help you indicate. So in 16, I had the value 4. I had 7 here. No, yeah. What I do here?
3.
Oh, sorry, 3. Yeah, you're right. 3 and 7. I was like, why is it 10? So it's 3 and 7. And then this value was 0. And then it updated the results by writing back, and it became 10. So this function could be k equals I plus j, where 16 is divided by S0 and MEPS plus S1 equals S2, because the S0 is the 16th register, and then all the rest of those are offset. We'll learn more about that next section. So we just showed the physical implementation of a 32-bit full adder where we grabbed it from the local register copies, added them, and then put it back in the register. Does that make sense? What's happening here? And then I show the results here. So I now have my printout here. Value in the register is, this was 16, because remember I had that fprint function where I wanted my read register result, and then here's the actual result, so it successfully got the value. The second value in the register is 17, and that value is 7. And then addition results, I had that function printout, so read store, carry out is 0, and sum is 10. And then updating register 18, I printed out that I wanted 18. And then I probably didn't need to copy and paste that again, but as you can see, it worked. So, C programming 4.9, which you don't have to worry about. for a little while. Writing a program that initializes 32 registers from a text file as shown in class. Then using your ALU that you designed in 3.10, show that you can add or subtract. So I've done add in class, right? So there's a specific way I showed you in a previous section on how to do add and subtract. You're going to be doing a 32-bit full adder subtractor. You're going to take that and show that you can update values from a register and places the result back in the update register. You must use a reg-write rule to protect the write register, which we've done in the function that I've done here. Meaning if register write is 0, then the result should not write to the register. You must demonstrate this in your result. So what's the simplest way to do that? So if I'm using that function here, let me go back to where we updated in the code. So here I have this write to the appropriate register. So if I wanted to add in a control signal, register write, that only allows this to happen if register write is true, what would I do? If it's true, do what? I want to write, so yeah, it's an if statement. I just put an if statement if reg write. And when you get into data path design, you're going to discover that having these kind of little caveats in there are going to become very helpful. So now we've designed memory, and now you'll have 2/5 of the data path already done by the time you're done with your second assignment. Okay, so let's go back down here. All right, so this I wanted to quickly go over this concept of one-hot encoding because I've already kind of shown an example of it already today in lecture where we have this value and then I have a 1 and all the rest are zeros. So we're doing that in both this as well as we're going to talk about shift left and shift right registers here in a moment. So 4.18, one-hot encoding is a method of designing sequential circuits where there's a state variable for each state. So if you recall, in finite state machine, we had like 2 states. And here we represented, if I had 1, 2, 3, 4, 5, and there's some sort of weird coming and going here, right? You can represent this, since there's 3 bits, we're using binary encoding, you could use that representing 3 bits, but there are pros and cons to that, and we'll discuss that in a minute. So one-hot encoding is a method of designing sequential circuits where there is a state variable for each state, and the current state is represented by a 1, and the rest are represented by 0. And so this comparison of binary, gray code, and one-hot encoding, I'll give you a nice little hint. So encoding of states, flip-flops needed for end states, advantages and disadvantages. So here I've given a 4-bit example. So binary, it's 0, 0, 0, 1, 1, 0, and 1, 1. Gray code, it's 0, 0, 0, 1, 1, 1, and 1, 0. Why is gray code designed that way? How's that? Race condition, right? And then one-hot encoding, S0 is 0, 0, 0, 1. S1 is 0, 0, 1, 0. S2 is 0, 1, 0, 0. And S3 is 1, 0, 0, 0. So you see how it shifts like so? So the flip-flops needed for each stage, log 2 of n, log 2 of n, and n. I have an answer.
One hot not start with 0, 0, 0, 0.
That's a good question. Why does not? go back to the definition of one-hot encoding. Yeah, so this means that this is 0. If this column is 1, that means we're starting with state S0. If this column is 1, it's S1. If this column is S2, and so forth. Yeah, it's a good question. I just wanted you to process the definition. Right. All right, so advantages and disadvantages. For binary encoding, pretty much your only advantage is low area. So here, by reducing the amount of time and reducing the race condition, we have lower power because race conditions consume power, and noise only due to 1-bit switching, meaning that you just got 0 to 0, 0, 1. So that time in a digital circuit where you're going like here, that's what I mean by the noise. Just these moments in between 0 and 1. Now, the benefit of one-hot encoding is that it's fast. It has a lot more area, but it's fast, fast, fast. And it's used in FPGAs. So in 386, when you code in VHDL and you're starting to do all of that, you're going to be using one-hot encoding will make it run really quickly. It may take a little bit of area, but the projects that you'll be designing in 386 will not require a supreme amount of area anyway. So your goal is to just make it run fast. And then disadvantage, increased noise due to multiple bit switching, which creates our race conditions as well. And reduced speed, so it's slower. And because we have to worry about race conditions, you have to make it run slower in order for all the timing to be proper. The next state, logic F. So here I'm talking about how most of the time it's low power, but occasionally we're going to get this power spike, meaning that if we kind of get to 1, 1, 1, 1, 1, 0, eventually we're going to get to this point where we're going to get to this, how do I explain this properly? Increase power and reduce. Oh, I see. Okay. So in binary encoding, where we have these flip-flops and it's going to change here, and we get these race conditions because everything's updated to a certain speed. And so in gray encoding, it's dependent upon the previous flip-flop. And so sometimes where your power consumption occurs is the difference between this power consumption and this power consumption is you have the clock going through, so it's only being affected by the clock. Whereas with gray encoding, you're actually manipulating your D input or your toggle flip-flop or your J or K flip-flop, however you're planning on manipulating it. So those particular switches happen to consume more power, but in general, they consume less power overall. And then last, certainly not least, in one-hot encoding, you just gain this large amount of area. So, does anybody have any questions before we continue? You guys seem unusually beat up today. A lot of exams this week, because that's... So, I want to get to this concept of shift left and shift right logical. So I've kind of alluded to it a number of times about the whole idea about multiplying or dividing numbers by binary values. And so if you think about it, you have 120. If you're doing it in decimal and you have 122 and you want to multiply it by 10, you just add a 0, right? Multiply it by 100, you add another 0. Multiply it by 1,000, you add another 0. If you're doing it in binary, here I give the example of 120. If I want to multiply that by 4, I'm sorry, 15 times 8. So this 15 times 8 is just 2, 4, 8. And now I get 120. And so when we get to this concept of byte encoding, you're going to each value in the array is going to correspond to 4 8-bit bytes. So array of 4 is actually going to be 4 times 16. So it's going to be 16, 17, 18, and 19 of those bytes. So we're going to be using that to do this. To be able to do this, we got to worry about this concept of shift left and shift right logical. So in MIPS, and so now we're going to start going into the format of MIPS instructions. I've posted the MIPS green sheet, which has all of the instructions on there corresponding to what AND instructions and subtraction instructions look like. So we have some sort of initial register RS. So that's a value corresponding to which register I want. And then R corresponds to this actually corresponds to the full value of the register, right? So you have actually gone over C code that shows you precisely how to do that. So remember, we allocate the memory, we create the registers are loaded in using our input text file, and then I have this 32-bit value, right, that gets the register. That's RS, where one of them is a 1. And then I get the result using the read register portion of it, right? So that gives me R of S. So that's what that means. So then what I do is I have some sort of shift amount value. The shift amount is going to be a one hot encoding as well. So it's going to tell me how many bits I need to shift. So what you can do is you can use a for loop to code. And you go 0, do I continue to shift? Do I continue to shift? Do I continue to shift? And then if I have a 1, then I shift that many, right? And if all of them are 0, then you just never shift. And then shift right, so then we take the resulting value and then we store it in another register, RD, destination register. And then for shift right logic, we're going to take RS and then shift right by that shift amount, which is the same concept of the bits, and then store it in another register. And so I've gone over this example of 15 times 8. And so here I have the initial function for shift left. So I've input a 32-bit bool array. I've input a 32-bit shift amount. And then I have I've created this bool shift left or right. So you can actually make sure you're shifting the correct way. So I have indicated false means left. So when we go in there, right equals true. So shift amount equals shift amount. You can do this in one of two ways. You can actually iterate through, or you can create an integer. I'll show you that code in a moment. If it's shift left or right, basically what you're going to be going through is you're going to start at the bit. You're going to go all the way from I is less than or equal to bits minus shift amount, I plus plus, and then the array of I is equal to array of I plus shift amount. So basically what that means is I'm taking my input array, right? And let's say I'm shifting by 2. So now array of I is equal to array of I plus shift amount. So I want these to be in my next one. So this is 0, 1, 2, 3, 4, 5. So array of I of 0 is now equal to 2. Array of I of 1 is now equal to 3. Array of I is now equal to 4. And then it's 5. So it gets to this point, and the reason why I say bits minus shift amount is then the rest of these should just be false. This code here, I equals bits minus shift amount, starts here. I is less than bits. Array of I is equal to false. So I'm just putting a bunch of zeros there. And then in your part of the assignment, I've indicated if it's true, that means you're going to shift right logical. So as part of your assignment, you're going to be updating that part of the code. So you could call this SL, you could call this shift, whatever you want. Shift logical. Oh yeah, SL is shift logical. So you can use that to indicate shift left or shift right. Because when we start getting in control signals, you're going to see that there's a 1-bit difference between shift left and shift right. And you can just use that bit to indicate which one, so you don't have to write multiple functions. And so, see, here I've indicated I have this SL test. Bool value, I've allocated bools, initialized them with false. And then I have this input value that I've declared. Then I have my char to bool array. Now I have a set of bools in value. And then fprintf shift amount is going to be that. Oh yeah, bool shift amount is a value that's being passed to the function. So we're passing the function. I'm just doing this as kind of a way to print it out. So remember, when you're doing your coding projects, I want you guys to indicate to me how your code is working. So when you see what I'm doing here, I have a shift amount. I've proven that it's gotten to the function and it's properly being received. And I have my initial value, which is printing value, which is this value, right? And then I do initially SL or R is equal to false. And I pass into our SL function that I've just done, value, shift amount, SL or R. And then I print the final result. And when you see the print results, you'll be able to see the difference in the shifts. And then I've created another value here. I've put it in value versus value input. And now, in my next step, I have done SL or R is equal to true. So I had some code in there that I didn't show you, which actually will do the shift right logical. Pass it through. Value shift amount SL or R. So now it's true, so it's going to shift right. And then it's going to print the value out. And then I free the value that I allocated the memory in the beginning. So let's take a look at the result in main function. So I have a bool shift amount here that I've allocated. First, I indicated that I want to shift left, shift 2. And so this will shift the amount here. And then I do a shift 4 and do the same thing. So then now I'm going to test to see what happens. I do shift left 2 and then shift left 4. And then shift right left and shift right 4. So, and then I free shift amount. So now I have my, remember I did it twice here. So I have my initial value. I shift left by 2. And as you can see, when we do shift left value, see how this 101 is shifted over? This one is shifted over by 2. This one is shifted over by 2, and so forth, right? And it ends here because this 0 shifts there. So we've done it properly. And then shift right values, you can kind of see how, when I get rid of all this, see how everything's kind of, you compare it to the initial value here, so you see how it's shifting right by 2. This value is now shifted by 2. This value is now shifted by 2. We do shift right. Now I do by 4. As you can see here, it's gone over 1, 2, 3, 4, 1, 2, 3, 4, and so on. And then in our function, we set that initial value before. And so when we look at shift right value, you can see that these values here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, we have shifted by 4. Shift right here, we have the initial value, 1, 2, 3, 4, 5. We shift here, that means we've properly shifted right and properly shifted left. And so 4.10, which should be the last part of So you're going to design and test a structural 32-bit shift logical structure using one hot encoding that performs both shift left logical and shift right logical. So you're basically going to take the code I wrote and you're just going to try to iterate through it to be able to get shift right. Does anybody have any questions about that? All right, so let's start going into section 5. So now we're going to start building this into C to MIPS assembly to machine code. So right now, in one of the course objectives, we discussed know the relationship between a hardware architecture and a computer's assembly language instruction set. So it kind of started to allude to it. I showed you an assembly language instruction for shift left logical and shift right logical, correct? So we're going to start going into how that is actually working, and how that's actually working, how that's done. So the 5.1, I've formally defined registers here as storing bits of information in such a way that systems can write to or read out of all of the bits simultaneously. You have already seen code that shows you how to do that. Any MIPS instruction has 32 bits. Any MIPS instruction may have one of the following 6 fields. So this is going to be how we're going to see how all this information, what we're doing is we're taking a 32-bit instruction and we're now breaking it down to be able to determine how information is going to flow through the data path. So 5.2, the first portion of every instruction in MIPS is known as an opcode, and it's often abbreviated op. So that's the basic operation of the instruction. That tells me what's the basic thing you're going to do. Load word, store word, R-type instruction, branch, jump, it's all there. The next 3 are register source, and register destination operands. RS is the first register source operand. So here, remember we had R of RS, so that register source operand is that 32-bit value telling me which register I want. RT is the second register source operand. And RD is the register destination operand. And then I have this shift amount, possibly in the function. And then last is actually funct. So function, select specific variants on the opcode. So if you recall from section 3, I talked about how we have this 4-bit input to the ALU, right? So you can have 16 potential functions. And that there's this 1-bit difference between add and subtract. That comes from the funct portion. If you recall from the TGO from section 3, I had these values going to the ALU, and then I had a second truth table where I had function values coming in. There's a 6-bit value. That's this. So you'll be using that TGO to be able to build up your data path even further. So let me scroll up past 5.2. So 5.3, oh wow, I really screwed up the numbering here. Well, that's why I have Word document. Give me a split second here. So this should be 3, and this should be 5.4. So they're all going to be off by 1, but I'll fix them in real time. Okay, so there are 3 types of instructions in MIPS. We have R register type, immediate type, and jump type. All right, that's much better. And for those At least I know you guys like the hints. You can expect this to see this in the future as well. Register is used for instructions that perform an operation on two register values and places the result in a register. So I have my two source registers, RS and RT. I do something in the arithmetic logic unit, and then I put them in value RD. So I might be able to zoom in a little more. So they're all 32 bits. So opcode is going to be 6 bits. Let me go to zoom in just a little more. Yeah, that should do the trick. All right, so opcode is always 6 bits. RS is 5 bits. Why do you think it's 5 bits? What can I represent with a 5-bit value? I think I heard somebody say more confidently. 0 to 31, right? And so what would I want to register? What would I want a solution to question before I actually ask the question, right? So I want to use this case. I can convert this 5-bit value to a 32-bit value, right? And once I have my 32-bit value, I can use one of those values to indicate which register I want to write to or read from. So what you would use here is a 5 to 32-bit decoder. You're all familiar with decoders? No? Well, because I'm creating some TGOs and teaching you decoders. All right, so 5-bit RT. So basically, a decoder, in short, is I take in a 5-bit value. So let's say 10101, right? So I have 16, 20, 21. So what I do is I'd have some sort of 32-bit value on the output, where let's say this was 21, where that would be the 1 and all the rest of these would be zeros. So that's known as a decoder. And an encoder does the exact opposite. So you'll design one of those so you can take the instruction, decode the 5-bit value, takes a 32-bit value out, and then you just plug it into your register function. So immediates are used for data transfer instructions. So 6-bit opcode, 5-bit RS, 5-bit RC, and I have a 16-bit number. So, for example, let's say I wanted to do a load word instruction. I've told you about these load word instructions, right? And then I have, let's say, I'm sorry, let me write it over here. Load word S0, comma, 8, S1, right? And so I'm taking my source register. RS indicates that I want, that's my pointer. And then my offset is physically here. So if, let's say array of 2. So what I'm saying is my S1 contains the base pointer to the array element. And then I add the offset that I calculate. In this case, 2 is multiplied by 4, and we get 8. And then I store the value in RT. So that's what a pointer is physically doing. And then last, we're jump address. So specifically, you want to be able to jump past certain instructions. So branching loop is an immediate instruction, so that's using if statements. But jumping means, let's say I'm doing a for loop, right? So I'm doing a set of instructions, and then I get to a specific point where I don't want to keep doing the instructions past the loop. I want to go back to the top, right? In order to do that, I use an instruction called a jump instruction. And the jump instruction includes the exact location of that instruction. And we'll learn a little later how to convert this 26-bit value to a 32-bit value. All right, I want to see what's. Oh yeah, so we'll do 5.4, and then we'll do. I'll call this 5.5, and that will be the conclusion of today's lecture. Okay, so 5.4, I added this TGO specifically because I get a lot of confusion about what RS, RT, and RD are. RS is a source register for all R and I type instructions. RT is a source register for all R type instructions and a destination register for all I type instructions. So for example, if I did J equals I plus 5, I would use an I type instruction because I would represent 5 using the number. RS would be represented the register of I, and RT would be the register of J. And then RD is the destination register for all R-type instructions. So does anybody have any questions about this? Okay, so 5.5. So what this chart says, and this is where we're going to end. So to meet, where'd you all end? You ended at 4.6. So 4.17 through the end of chapter 4, and then 4.17 through the end of chapter 4, and then 5.1 through 5.5, the TGOs for the homework. So we have 32 registers. We have the initial 0 bit. The first register is going to always contain the value 0. And we're going to go into examples of when having the value of 0 is important, specifically in comparison instruction. Assembler temporary is, these are all dollar signs, by the way, is 1. You'll rarely mess with this. V0 through V1 are values for function results and expression evaluations. So when you do a function, you're going to use A0 through A3 for arguments. So you can pass pointers. And then when you do your result, you can use V0 to store your result. Eight through 15 are known as T0 through T7. They're temporary registers. They don't contain an actual variable, but they use temporary in-between instructions to be able to store those so you don't overwrite variable. S0 through S7 are 16 through 23. Those are known as saved temporaries. And then T8 through T9 are temporary. So saved temporaries means there's actual variable associated with it, but it's temporary because cache is always, it's not as volatile memory. You're not going to save it long term. 26 and 27, we'll be going into this and we get to error handling reserved for the operating system's kernel. I'll tell you what values you're going to be putting in there before your project. And then for those of you who've dealt with coding projects before, global pointer, stack pointer, and frame pointer indicate where your function is, where your function is on the stack and where your function is on the frame. That's a lot of operating system stuff. And then 31, this return address, you're going to be using RA31 to be able to do jump instructions to indicate the return address of a function. Okay, so you call a function, you pass the variables, you pass the arguments, and the last thing you're going to do, JRA, which jumps to the return address, which indicates where the next instruction is that you want to complete in your function. So we'll be going over jumps and all that in a bit, but it is time to dismiss all of you. So rest up, do well on your exams. See, McKinnon and Robert emailed me, so you guys are fine. Christian Riley. Yes. Same thing here. You're a couple minutes. You're right.
I can get
No, I can't. I'm not, by law, I'm not permitted to do that.
Oh, was this the last TGOs?
Yeah,
I was absent.
Okay.
Yes,
Yes, I did.
Would you be in our office maybe about 12:30 or so?
Yeah, I'll be there.
Okay.
But you kind of have to make a quick conference call at 1. So if it's a quick question.
Narrowed it down to one line.
Perfect.